So how do we store things? How do we store things in a priority queue? Well, information is going to be stored in a key value pair, right? In a language like Python, where you can absolutely express it like this, yeah, a tuple, right? An ordered pair is probably the right way to go. But they're stored associated with each other, immutably associated, where the value is the value of interest and the key is the priority of that value. Okay. From our perspective as computer scientists and developers, we are very interested in the key because the key is what makes this whole machine work. But the user is interested in the value. The value is of interest to the user, and the key's just there to make the thing work. So to go back to our trouble ticketing system, the key is what is bug, right? Top, high. These are your priority levels. Okay. And this is useful, but this is the actual request, right? So we need to hold on to this value. This is of crucial importance to the user, but it does nothing in the code to drive the behavior of our system. Okay. And we'll talk more about that as we go along. Okay, so we have a priority queue. What's our backing data structure going to be? Now, if you're shrewd and you know how to metagame, you can probably guess where we're going to end up. But to be clear, we can use anything we want. And the naive example would be, well, let's just use a plain list. That's what we did for a queue. That's what we did for a stack. Okay. But then we want to get things out of the queue, out of our list, based on the priority. So we need to then ask ourselves, okay, well, if we're going to put it in a list, do we want that list to be sorted or unsorted? And if we want it to be sorted or unsorted or whatever, what's the performance of those options going to be? So let's take a look. So let's consider this unsorted list. And to be clear, we will frequently display heaps or queues or priority queues or examples like this, okay? And remember, we need a key value pair. So what's 4? What's 5 here? What are these? These are the keys, because remember, the keys are the structural things. They're the things that drive the machinery. When it comes right down to it, from our perspective, the value is just along for the ride. So if we draw it this way, assume that there is some value associated with each of these. The nature of that value, from our perspective, is unimportant at the moment, okay? Also keep in mind, and don't forget, that the key and the value can be any arbitrary type that has, the key can be any arbitrary type that can be ordered, and the value can be anything. The value could be, you know, a data stream, right? It could be whatever. The key has to be able to be ordered because we have to be able to compare them. So we have 4, 5, 2, 3, 1, right? These are numbers. These are integers, to be more specific. They could be floats, they could be strings, they could be any object that is able to be compared and ordered. So if we have an unsorted list, inserting is easy, right? We can just put it at the beginning or the end, right? And that's big O of 1. If we insert a new value, we could put it up front, we could put it at the end. It's super easy. However, finding the next element is going to be hard, because Like 1's at the end. But 1 could be at the beginning, or it could be in the middle. So in order to find where our minimum key is, we have to sequentially search the entire list to find the minimum element. Conversely, we could use a sorted list. So now the next element's always at the front. That's super easy. If we insert, if we add 0, right? Well, that's going to come up here. So it's always going to be big O of 1. That's going to be easy to find what we need. But now when we insert 3.5, well, we got to find out that it goes here. So inserting is going to be a linear process. So if we use an unsorted list, we're making our insert easy, but our find hard. And if we do a sorted list, we're making our find easy, but our insert hard. There's got to be a better way. And there is.